Second speaker organizer this morning is Michael Roeckner from Bielefeld, and he's going to talk about stochastic variational inequalities applications to a total variation flow perturbed by linear multiplicative.
Okay, thank you very much. So thanks a lot to the local organizers for letting me speak here. And topic is there. It's quite a long title, but anyway. So it's joint work with Viorel Barbu, and this is the content. So it's first of all introduction, and I will explain you about the framework, and then I will define, in the stochastic case, what is variational inequality. So stochastic variational inequality is the abbreviation, and then the main existence and uniqueness result for the model that we are considering. One of the main tools is to transform the equation into a random PDE. If there's time, I'll tell you a bit about the method of proof, and then we'll present also our extinction result in finite time, and if there's time, also a little bit about the proof there. But let us see how it goes. Okay, so we are interested in this nonlinear diffusion equation. So it's just a PDE with a very, very singular drift here. So the sign here of the gradient, so sign is a function that goes from Rn into the subsets of Rn, to be precise, and it's simply the same as the sign function if n is equal to 1. So that means you just take if n is equal to 1 plus and minus 1 if you're outside 0, and at 0 you take the whole interval. So in multi-dimensional case, you do exactly the same. You just divide by the norm, and then you associate to 0 the entire unit ball. So that's the usual way how to define the sign function on Rn, and this is a multi-valued function. So really what I should have written here is somehow an inclusion here, because this is set valued, so this is a more heuristic expression. Okay, then we have directly boundary conditions. I will say something about that, but in a generalized sense. I will explain this later in more detail. Initial condition is in L2, and that's very important. I will also come to that, why in L2, why not smooth the initial conditions. And this equation I will just label as PDE in all the talk. And the whole thing is on a bounded convex open set. Convex is also important. I will stress this later with smooth boundary. And we have Brownian motion here. So that is a linear multiplicative noise. But the Wiener process, let's say, on H here is a colored one. And how we write it is like this as usual. So if we have independent Brownian motions, so Ft Brownian motions on this probability space. Ek are the eigenbases of the Dirichlet Laplacian. Mu k are numbers. So to make this converge, it will be a Q Brownian motion with a trace plus covariance. So we have this infinite sum. In our previous work on this type of equations, where we do the transformation to the random PDE, we always took finitely many modes, but here we take infinitely many modes. It's technically really hard to go here to n equal to infinity, but we worked out all the details in this paper, which is on archive, so you might check. Okay, so this is the standing assumptions on the mu k, the convergent factors for the noise. So this is the first assumption we have, and also we need something for, just tell you the truth, we also need something on the gradient, so we have to take just mu k small enough in order to, this is true. And then if you look at the this Brownian motion for fixed psi, it's a real value process, which is of course a martingale because of the convergence in, let's say, L2. And then if you look at the bracket of this martingale, then it is just this mu psi, so this summation mu k squared, k squared. So it's a Brownian motion which is not standard, which has a covariance, which has a sigma which depends on psi. Yeah, but otherwise, well, that's one of the main features here, that we can really evaluate at psi, and in fact, this is in psi even C1 by our assumptions. Yeah, but that is, but not more. Okay, so that's the situation, and then a little bit about the modeling. So I'm not an expert on this modeling a lot, but I read a little bit into the subject, and Viorel explained a lot to me. So nonlinear diffusion theory, this SPDE, which I label my main equation by, is derived from the continuity equation perturbed by a Gaussian process proportional to the density of the material. So it is this J would be this divergence term, and then J is the sign. Sorry, it's not the divergence. Is the sign, of the flux of the diffusing material. So that is and here's the references for that, but I go very quickly here just to show you it is an important model. It's also relevant in mathematical model for faceted crystal growth under stochastic perturbation, important in material science. And so it's a differential gradient system. The corresponding convex function is in general non-differentiable potential. Okay, and then this is my main motivation, so it's a particular paper by Lyon. So other recent applications refer to image recovery. So this is a reference also Aaron Yippiel from Purdue University. And if X is in L2, so in fact X in L2 can be interpreted as the blurred image on this set O, and one might find the restored image by solving this singular diffusion equation with this initial condition. And then of course you do not want to assume any smoothness in space about the initial condition, because the image is sort of in a not nice form, yeah. So it is not somehow smooth in the spatial variable. Yeah.
But just to get an impression of it, if you start with a like smooth bump or something, what is this? If you just take the deterministic expression, you start with a smooth bump.
Okay. The exact statement is you start in H1, then you stay in H1.
Okay. I mean, in terms of dynamically, what does it look like? I mean, how does it move if I start with a bump? You know, what do the level sets do?
It's not a level set equation.
It's not
I don't think so.
It's not the mean curvature equation, so it doesn't keep the height. So you would have to take the gradient x in front of the divergence term.
That's different.
This is the divergence.
The divergence is outside. It's different from the porous media. So it's not the porous media. Yeah? It's really completely different. Okay. And so in deterministic form, this is so-called total variation-based image restoration model, and rises naturally in this concept as a perturbation of the total variation flow. This would be the solution of the deterministic equation perturbed by a Gaussian noise, multiplicative noise, which explains the title of the talk. So this is also my favorite form of writing it. So instead of writing here the sine function, I rather write this quotient, and we should remember that if x of t is 0, it's the whole unit ball what is there. So it's a multivariate equation. Okay, and we studied this equation before with additive noise. Yeah, so this was the equation. So I'll just put the divergence term on the left-hand side in this paper in Siam. But so in there we proved existence and uniqueness for so-called variational solutions, and I will explain in the sense of stochastic variation inequalities, and I will explain this in a moment. But in the multiplicative, and only for n between 1 and 2, and here we have existence uniqueness result in all dimensions in the new paper. And the multiplicative noise case, we only proved existence, and it seemed it was extremely difficult to prove, and it seemed almost impossible to prove uniqueness by this approach in the multiplicative noise case for arbitrary initial conditions. So I want to stress this. It's very, very important we start with x in L2. Okay, so there is work if you start in H1. I mean, then sort of machinery of a monotone equation, nicely developed by Benjamin, and so these are my two former students, Benjamin Guess and Jonas Tölle. So they apply this big machinery also to find a solution, but for initial conditions smooth. And our approach is completely different because we want to have arbitrary initial conditions. Okay, so that's the new paper. So we prove existence and uniqueness of variational solutions, which I will define in a moment precisely in all dimensions and all initial conditions. And the main difficulty, as I said before, is this. And if n is less or equal to 3, we can also prove extinction with positive probability in finite time. Not with probability 1, that's it's inherent in the techniques that we develop for proof existence in the stochastic case, so we can only prove with positive probability. But in any case, it generalizes the deterministic case in these papers. And the n less or equal to 3 comes from we really have less of a certain lack of regularity of the solution that we cannot overcome. So we don't have that the solutions in this are in W1P for some P in order to apply Krylov's Ito formula for the LP norm. So there's really a threshold exactly if n equal to 3. So that all interpolation inequalities exactly break down at that point. So the stochastic term here really causes a lot of problems. There's really no comparison with the deterministic case, because in the deterministic case you just can apply the very strong machinery of monotone, of PDE with monotone coefficients, also multi-valued, but in the stochastic case you have to do approximations, and that is really much harder. So you cannot just do it as in the deterministic case. So just some notations. So LP is a usual LP space with the P norm. In my case, O is in R, the subset of R capital N, and the N norm, where N is the dimension, capital N norm will be important for extinction. So just want to mention this already here. Then these are the standard Sobolev spaces. So 0 refers to directly here, and we take always this norm. Not we don't add the LP norm. Yeah, this is for the more convenient norm in this case, and then we use the usual notations for W12. We take A1, W2 to H2. So now let me recall quickly what we also need. That is the main tool here, namely a space of bounded variation functions. So if you're given any function, so it's called a bounded variation, if this quantity is finite, so which is defined simply, I mean, what you do here, if you look at the derivative of the function u in the sense of distributions, yeah, and then, well, if it is a measure, then you can look at the norm. I mean, you look at the dual norm given by the test function space. So the dual of the an infinity norm, and if this norm is finite, then it is a bounded variation. And since it's a measure, of course, this is just the total variation of the measure. Yeah? Take just formally over the gradient. So you try to find the gradient of u. You know, you write it down in the sense of distributions, and then you realize the gradient of u is really a measure. It's a distribution of order 0. Yeah? And then this is exactly the total variation of this measure. And if you have a function for which this total variation is finite, then you call it a bounded variation. This is just for those of you who have never studied bounded variation function in higher dimensions. And of course, if u is in W11, this is just the L1 norm. Yeah, it's just the dual norm of the infinity, if you like. Okay, and then this is the usual notation for bounded variation vanishing on the O. And now this term that appears in the PDE, in the SPDE, is nothing but the subdifferential of this du. Du is a convex functional. If u is in W1, it's just this integral, the L1 norm of the gradient. So this is just a generalization of this is a convex functional. So you can think about it subdifferential. And in fact, this guy is multi-valued, as I say, but it's exactly the subdifferential of this du. No, and this is, I explain here a little bit just to make you a bit more familiar with the framework. And I also would like to point out an error in this paper in Siam, which we're just sleeping a little bit there, and I will explain in a moment why. Okay, so first of all, we extend this du, the bounded variation norm, to all of L1 by just putting it plus infinity. Else, on L1 minus the BV function. BV is always a subset of L1 by definition. And then what we do, we take the, so what we did in the paper in Siam, we forgot that this is not lower semi-continuous. Okay, so in that paper you always have to replace the phi 0 by the lower continuous envelope. So we take the lower semi-continuous closure in L1. So just by taking lim inf at every point, so we wrote it here a bit intuitively how to calculate this closure, then it becomes lower semi-continuous. So in that paper, you always have to replace the phi we defined by this guy. And this was pointed out to us by Jonas Stolle after I think he saw the paper for the first time. He said immediately, be careful with that. Okay, but this is no problem. So it's just a matter of redefining this. Because what comes out now, if you take this lower semi-continuous envelope, I mean, you can find it, for instance, in this nice book by Artouche and Boutatz and Gérard. What comes out is that you see that this, now these functions do not longer have a trace 0 on the boundary. So what comes out is this guy. So you get a boundary term, which is not 0, with respect to Hausdorff measure if you do this construction of the lower semi-continuous envelope. So therefore, that's what I said at the beginning, we have directly conditions for our equation just in a heuristic way. I mean, what we really have is functions that do not have 0 boundary conditions. Yeah? But we always, because we have to take this lower semi-continuous higher, this is the price you pay, but we have nevertheless the boundary condition still in a sort of generalized sense. And then we put the whole thing on L2, so we basically restrict this now to L2. Yeah? We just define it like this, plus infinity elsewhere, because we want to work on the Hilbert space. And this is the remark concerning the directly bounded condition. Okay. And then you can just define the subdifferential of a convex functional as usual. So you take, in the Hilbert space, it's very easy to write down. You take all eta and L2 so that this is true. So that is a set. So you assign to a point U a set of vectors that are sort of the generalized gradients. Yeah? So it's a whole set of gradients, if you like. And so the domain of this function phi, so the PSE is just where this is finite, so it's just a BD function in L2. And then it turns out you can actually calculate, I mean, these vectors, so these are vectors in these functions in L2, their divergence of L infinity functions less than 1, where exactly this supremum is attained. Yeah? So you take the supremum here, and it's attained exactly at those phi's, which I call Z. And these are exactly all the sets in the subdifferential. Yeah? So exactly here this thing is attained. And then you can write heuristically, and you see, I mean, this is the phi u. You can write heuristically, this is the same as this, but just dividing. And you see, you're just dividing, multiply, and you just do integration by parts. And now, rigorously, if you think that in terms of distribution, so this measure acts on Z, it's a vector-valued measure. So that's exactly what it should be. And then now the definition of divergence is that, okay? And then you see this Z is a section of this multi-valued thing. Yeah? So you just take a section, or possible sections with this, all these properties. And so from that point of view, this subdifferentiable is this set. Yeah? So that is multi-valued operator. Okay, so that's a thing to remember, because then we can, first of all, we can rewrite the equation like this. So this thing, divergence grad u divided by grad u norm, or grad x norm, is exactly this d phi. So you can write it this way. And here, really express the left-hand side is multi-valued. And in the deterministic case, if this is not there, so here's just 0, then this falls in the general machinery of monotone multi-valued equations. And then you can solve the equation by, for instance, Prandtl-Liggett, one of those standard things. Anyway, so now in the stochastic case, we have to work a little. So it's not like that. And in particular, if you take arbitrary initial conditions in L2, there is no standard existence here that applies directly, so we had to do something new. And you see, these are all with little primes here, just the different versions, whether you write it like this, whether you write it with a sine function, or just in the gradient form. Okay, so now we are going to formulate that as a stochastic variational inequality. So that is the new thing, which we already started in the SIAM paper that I mentioned, but now we really worked out better the details and the general philosophy. Okay, so let me first of all define now what is a stochastic variation inequality. And since now book of Luigi Savare is very popular, I mean, you know that you can formulate these stochastic variation inequalities instead of the corresponding evolution equation also in metric spaces. And the first step to go to the metric space is to reformulate the evolution equation as a stochastic, as a differential inequality on the Hilbert space, and then you just refer, then you just work, of course, to carry it over even to metric spaces. But it has, to the best of our knowledge, not done in the stochastic case. It's a variation inequality formulation, and so let me explain how to do that. Okay, so let's say we fix a time for the moment, and we have a stochastic process on 0t omega on underlying probability space with values in L2. It's said to be a variational solution, so now we have to be careful. Variational solutions are also called the classical solutions for in the monotone framework. They're called also variational solutions. So we had the choice to call these generalized variational solutions, or to call these variational and the old ones classical variational, and we opted for the second. So we call this one variational and the other, for the evolution equation, classical variational solutions. Okay, so if the following condition holds, so x, of course, at t depth, it should be continuous in the state space, right initial condition. The usual integrability condition, the minimal one, and then it should be, if I apply now phi, which is now the bounded variation, I mean made lower semi-continuous, so the solution should be L1. Okay? So I will not write this guy, I avoid to write this guy, because it is very difficult to prove that this is in the domain of d phi, even if we have a good initial condition. This is work to do. Yeah, but for L2 it's impossible, it's simply wrong, I guess. Yeah? So therefore we avoid this guy and we write this equation more in an inequality style using phi and not the differential of phi. Okay, so for each, now here are the test processes, like the test functions in the deterministic case. So for each ft progressively measurable process G and each solution Z of this equation. So that means G is like a label. You have lots of G's. And you take all the solutions of this equation. And important is here with multiplicative linear noise. So here the noise is reflected from our original equation. So these are our like test functions in Schwarz distribution theory. Yeah? We have now test processes. And we label by this G. And it's very important that this G is in L2 because probably many of you would now say, well, it's enough to have this in H minus 1 and you go into the variational framework because in particular, soon Z is H1 valued. But that's a very bad idea to go to the variational framework here. We need very heavily that this is function valued because we have to evaluate this at a point psi in the underlying state space. And if G is H minus 1 valued, like is usually in the variational approach, then we cannot evaluate. And that kills us. And that makes the problem with all this approach in the stochastic case that you cannot do it as you would like to do because it's very, very important that this is a function in the whole approach. Okay, so these are the test processes, and then we can reformulate our equation like this. So first of all, it has no resemblance with our original PDE. But let me go just one page further. Remember, this was the formulation of our equation using the subdifferential of phi. Forget the z here. This was the original equation, dx plus d phi xw inside. This formulation. Now you write this equation and you subtract. And you get this equation. Just subtract. You see you have z g dt minus z dw. It's exactly this equation in differential form. You subtract, and then you formally apply Ito's formula to this guy in this equation. And what comes? And then you take expectation, and then you come up with this equation. So which means if there is a strong solution, it is also a solution in the sense of stochastic variation inequality, exactly the same as in the deterministic case. Okay, so we have this formulation, but the good thing about it that if we write it this way, we can write it using the fact that this guy is the subdifferential, right? So that if we have with test processes, the subdifferential can be written as a difference of this part and this part. Okay? You just write the subdifferential by definition in inner product, and then you use the inequality. And then you come here, and the d phi is gone, you just have the phi. It's exactly the same as in the deterministic case. This is not due to us, but what is the only thing we have done now is to write a proper version in the stochastic case.
So why do you write expectation?
That's a good question. It seemed to us easier to write the expectation. Because you're right. I mean, because here you see there is exactly the definition of the subdifferential. If you take this to the other side, you don't really need the expectation at first sight. You're right. Yeah. Okay, so maybe one should also think about the whole framework without the expectation. I can really not say whether this is better, but it seemed to us easier. Yeah. Okay. Good. So then we have this inequality. We say we have a solution if for all these test processes Z, we have this inequality. And you see here is important that the G is not H minus 1 valued, because then you have to prove your solution is H plus 1 valued. Otherwise, this inner product in L2 is not defined. So in the sense of Schwarz distribution. So if you go here to a larger space, H minus 1, you have to prove the solution is an H plus 1. Yeah? And this is for arbitrary initial conditions far from being clear. So therefore, we have to take the G, so that is really due to the singularity of our nonlinearity, we have to take the GL2 valued, otherwise this thing breaks down already here. And that causes a lot of problems. Yeah, exactly this point. But this was the only way it seemed to be possible to do this. Now I call this SVI, stochastic variational inequality. Okay, so, well, you can always reformulate your PDE in another way, weaker form, and solve it. It's more or less a meta theorem. If you formulate it weak enough what you want, you find something that satisfies the equation, the inequality, or whatever you are down. So the only justification for this approach is to be able to prove uniqueness. This should so to identify the solution, and for smooth solution, it should be the original notion. Yeah? That's what you normally do. Okay, so let us now accept that this is a good formulation. Okay, and I said it's not what we construct is not a strong solution. If X is not good, then we will not have a strong solution. This would be the usual formulation, but we do not know whether this is inside there for arbitrary initial conditions. Okay, So here's the main existence result. This is now chapter 2. So again, our condition, bounded open set, smooth boundary, and for every x in L2, we can prove that exists a variational solution to the SPDE. So that means a solution to the corresponding stochastic variational inequality. Okay, and uniqueness, we need a bit more regularity in omega. It's not so bad. You say, okay, if you have a bit more integrability in omega than just L2, this would be the natural one. The solution is automatic in L2, but not in L2 plus delta. So we need a bit of delta to prove uniqueness. I think, but that is a price you can pay in the stochastic case. It's not really bad. Okay, and then furthermore, X has the following properties. These are the usual properties. So it's continuous in L2, and even in this space, so the usual space you would expect. Then this is true, it's also standard. You apply eta formula to the norm squared simply, you get this kind of thing. Then you have continuity in the initial condition, so in the usual way, because there is of course some monotonicity behind, some dissipative equation behind, so you automatically would expect this, and this is true. And the other thing is if the initial condition is positive, the solution is positive. So we develop general techniques for this, and they apply immediately to this case, so there's no problem. So, because this is sometimes, well, it has an interpretation of a density, so it should be positive. If the image is positive, you have, I don't know, pixel, whatever that you try to model by heights, and then these are usually positive and not negative. So, and then also the solution should be positive. Okay, and then when n is less or equal to 3, we can do the same thing in LP. So p equal to n, so we also have initial condition dependence in a continuous way. The soup inside here is very important, it's much stronger than outside. And the other thing is if we start with a good initial condition, then we stay in the H1 space. So with a start in H1, we stay in H1. So then also with the soup inside here. Yeah? Because otherwise the zero set would depend on t, and then you would not have a dynamics in H1. You would just have a dynamics which happens to be with probability 1 with a fixed time in H1. But this zero set of omega can depend on time. But here it does not depend on time. But this is only, this is only in the case when the initial condition is good. Okay, so this I said already. So main point is arbitrary initial conditions. So now I come to section 3, and I would like to explain one of the main tools that we use. And one of the main tools is to transform the PDE, the SPDE into a PDE. By the following transformation, you take y equal to minus wx. Okay? So remember, x is in L2, w was even continuous valued Brownian motion, continuous function valued Brownian motion, and so you can write this. Then you, and I want to stress this, heuristically apply Ito's formula. Then you get this equation. So the new variables, this the linear part, I already explained this some other talk about the porous media equation where we also did this. It's kind of a time-dependent ground state transform. No, I shouldn't say ground state, Dabou transformation. Yeah? You put something inside a function, you multiply, then you apply the nonlinear operator, and then you divide by what you have multiplied before. So it's kind of a generalized ground state transformation or Dabou transformation, but it depends on time. And the difficult part is the Brownian motion depends on space. So you cannot interchange with the gradient here. If the Brownian motion is real valued or n valued, the whole thing becomes more or less trivial. Yeah, and just take it, you can take it out of everything, and then it cancels. It's like an SVE, and things are very, very easy. But the Brownian motion depends on psi. Yeah. So therefore, this equation does not fall in any class that is known from PDE. Yeah, right away. Okay, and then we have this part. The mu, remember, was just a summation of the eigenvalue square mu k square. Yeah, was the bracket of the Brownian motion if you evaluate at psi. So now we would like to prove we have rigorously the two things are the same. Of course, in the sense of stochastic variation inequalities. This will be, of course, 1 point because you see I write it here for the original equation. And one can really prove this rigorously. And why is there a problem? Now, suppose everything would be a normal SPDE. You would say, well, it's easy. You just apply Ito's formula. But in which space do you apply Ito's formula? In which algebra of functions? Because this only defines an equation in the sense of functions, not real numbers. So it is not allowed to evaluate w at psi and x at psi because at x, what is x? It's xi. It's a solution only in an L2 sense. So you cannot fix psi and apply Ito's formula xi y's. So you have to really be careful what you're doing here. The trick is you take smooth function over xi, then you can multiply, then you can apply Ito's formula, and then you go to the limit. It's one possibility to prove it. There's also proof, and it's a bit delicate, I've not put it in the paper, that one can actually find a version of x which you can evaluate xi, and it's a semi-martingale for every xi outside the Lebesgue zero set. So there is such a technique, but the proof is incredibly complicated. I can show it to you, but it's not in the paper. Yeah? A little bit is in the paper. I can show you the point, but I don't want to spend too much time here. Okay, so you have to be careful. So now let us look at the equivalent random PDE, but now again as a variational inequality, because if I want to have the solutions equivalent, one is a stochastic variational inequality, I need to rewrite this equation as a deterministic variational inequality. Okay, and here's the definition. So again, x in L2, a process in here is a solution of the variational solution of the PDE. Now it's exactly analog. So it has a right path. Now we have to be careful. This should be L2. That's the x. So to have equivalence, we have a to the wi must be in L2. So also here, x was before. Here's a to the w, because that's exactly x. Yeah, if we put this to the other side. So this is the right condition. And then you look at the test processes. You also have to transform this equation properly. So look like this. And then you have the same type of inequality. Everywhere where there was a y is now e to the wi. Okay, and a z tilde where there was a z, always with this. And then you have exactly the same. So you see, sometimes when you go to a PDE, then people say, no, I can forget stochastic, I fix omega, I do all the calculations. And I tell them your constants blow up. You have no control of the constant if you just do a pathwise calculation. If you want to come back, no chance. And this approach has the advantage that we keep track of the omega just by the very definition of solution already, with the expectation. And maybe this is an answer to your question. To take the expectation here, we have sort of built in the definition the control over the omegas. It shows you we cannot forget the stochastics. Yeah? It is built in. Okay, and now this proposition, and probably have no time to go too much in the proof, but it will just show you a little bit. So x is a variational solution of the SPDE, so a solution to the SVI, the stochastic variation inequality, if and only if the y is a solution to the variation inequality. That's an if and only if. Okay, method of proof. What you do is you smooth out the singularity. Remember here you take the sign of the gradient. So you do such kind of a smoothing, you make it coercive by doing this. I want to ignore that in the future. That's just a little step to make it coercive. And then you have an approximation of the sine function like this. So it's the usual approximation, the Yoshida approximation of the sine function. Then you have a very nice equation which you can solve with the usual classical variational approach, stochastic variational approach. And the same for the corresponding equation here. And then you have to relate the two. And again, the statement is take a solution here, then it will be a solution of this. And I just want to show you how you prove that, just a little bit, where the difficulties are. So then there's a proposition, so first of all, for the approximating SPDE lambda. This is the approximating one, the little lambda there. PDE is the lambda, the approximating one. Then you have a classical variational solution for the approximating equation, first step. Second, if you do the transformation, then this will solve the classical PDE here, not in the variational inequality form. And that is the main step, to prove this really solves the equation. Yeah? This is exactly what I said before, is heuristically clear, but otherwise. Okay, what is very good now about this equation, I want to show you one instance why it is so good to go to this deterministic PDE. What follows immediately for this y lambda, if you start with the smooth condition, you will not only stay smooth, but you will be also continuous in the stronger norm. And we cannot prove this for x lambda directly. We can only prove it this way with y lambda, because y lambda solves the deterministic PDE, and we can use classical maximal regularity results from the deterministic PDE. And then, of course, this is an h plus one, an h1 multiplier. So this has the same regularity. The x has the same regularity as the y. So this is just one instance where you see why it is important to go to the deterministic PDE. Okay, and then in this case, then you have this usual energy estimates on the H12 norm if you start in H1. So on the level of the approximating equation, you can apply the usual machinery of monotone equations. So that's just one thing. And then you prove in the existence proof that these x lambdas, solution of this equation, form a Cauchy sequence, and you take the limit, and then you have to prove that the limit satisfies the stochastic variation in inequality, but that's quite easy. It's just kind of lemma of Fatou, more or less. It's very easy to prove that. Much easier than for the usual PDEs, SPDEs. There's always a problem. I mean, in SPDE, PDE, you prove tightness, you get limits, and the problem is always to prove the limit points satisfy the original equation. For stochastic variation inequalities, it's quite easy to do that. It's an advantage of the formulation. Okay, so the first I said is standard. Then the smoothness on y lambda is standard by deterministic. And now let me explain why is y lambda in fact a solution, so which I construct. So first I construct x lambda, I define y lambda, and then I prove the y lambda satisfies this equation. So I just want to show you what is the problem with the proof. To prove that y lambda satisfies the equation, it's enough to prove this. This is y lambda, e to the minus is y lambda. And you take a test function, comma, phi, and then you write the right-hand side of the equation on the right-hand side, comma, phi. So this is what you have to prove. Okay? But this inner product you can develop into an orthonormal basis. So you just use this. Okay? So now you have, but you know here, that this W satisfies this equation. So for every fixed x, this is a semi-martingale. So you just put this inside the integral and use stochastic Fubini theorem. So then you can express this thing as a semi-martingale. This is a semi-martingale, so you can now apply Ito's product rule to these real value processes. Let's do that. Okay, so that's the other one. Oops, it dies. It died. Okay. Okay. So do this for both, and then you apply Ito formula to this product. And now it's a mess, first of all, yeah? But now look, what is important, the stochastic part drops out. Now look at the stochastic part for every fixed j here. It doesn't drop out, right? It's different. But now think you take summation over j, then you get inside here the inner product of this guy and this guy. If you take summation over here, you get inner product of this guy and this guy, which is the same as that, and there's a minus. And it drops after summation. You can see it here, that it drops only after summation. The problem is, you have to show that this summation over j interchanges with all these sums and integrals and so on, but that can be done. Yeah? But on this level, I think you can see this doesn't drop out on the level of the components, but after summation over j, you see then you have the inner product of this and this, which is the integral of this times this. But here's the same, integral of this times this. So it just drops out. So that's the way how to prove this. Sorry, yes, it was too fast. The other thing I would like to mention about the method of proof is the last part. So I said before, this one comes out standard, which is right, but you have to check that this constant does not depend on lambda. So by standard methods, you just get this easily, but this C depends on lambda. In order to prove this is independent of lambda, we need a very, very important fact, and we were absolutely surprised that this is not known, because in the previous paper we even said everybody knows. And this is exactly this kind of inequality. You take the resolvent, maybe you know. So you take the resolvent of the Dirichlet Laplacian as a smoothing operator. We use that all the time in the entire paper. And then the question was, take the W11 norm of J epsilon u. Will it contract under the W11 norm? And this seemed to have been not known. And so Viorel and I spent some time to prove this, once we realized it's not trivial. And we could prove it easily in one dimension. We could prove it for half space. But when we wanted to go to arbitrary open sets by, just the local charts on the, then the problem is there's overlap if you take partition of unity. And that destroys generally such inequalities. So it was important to find another proof, and then there's in one case it's known, namely you can do the same in LP. So this follows from this. You just can prove if this is true, you take a convex functional, then this is true. If the u is in so H1, so L2 integrable, the gradient L2 integrable, you can take G just of quadratic growth, but if you have a u here, you can take any convex functional of any growth P, if this is an LP, so you get immediately the LP version of that. And it was known, this is known for P equal to infinity, according to an old paper. So then Viorel had the idea to simply contact Brisis, and he sent us a proof of this. And but he said also it's not known, so he did the proof. And there's a very important, very nice trick, which uses basically that certain term has to vanish on the boundary, and that has to do with curvature behind it. That is a geometric idea, of course, behind. And roughly speaking, well, it's okay if locally your boundary is convex. Then just this one term has a sign, it drops out, which is the bad term, and so we get this. And this is absolutely crucial for this last part of the proposition. Okay, now proof of the theorem I already said. You take the approximating processes, you prove their Cauchy, then you get a solution. And in order to prove uniqueness, and here's a misprint, it should be not S, it should be VI. The uniqueness we can only prove for the transformed equation, so for the variational inequality. By
Yeah, so why do you take this particular operator?
there are many other smoothing operators in the BV function setup, but they are not the control. Okay, they depend on u. You have a given u, then you smooth the u. We wanted an operator which is sort of universal for u, that's smoothing universal for u. This was absolutely essential. And therefore we took this one. And the semigroup, you could in principle also take the semigroup, but it does not behave as nicely as the resolvent. So we wanted to have the resolvent. And for the semigroup, this I think this inequality was proved by Diego Palara. He told me in one of the papers they have this for the semigroup, yeah, but not with Neumann boundary condition, not with Dirichlet. Okay, anyway, so the uniqueness, now what is the idea of the uniqueness? If you look at the variational inequality, we prove uniqueness there, and since it's equivalent to the other solution, we have uniqueness for the other. So here's the variational inequality. What you do is you plug in for the test function, for the test process, the solution itself, which you cannot because they are smoother than the solution. So you have to take your solution that you have just constructed, and you use that solution to prove uniqueness, which is sort of strange. In PDE, if you want to prove uniqueness, you cannot take the solution that you just constructed. You have to take an arbitrary other one. But in this approach, since you have all these test functions, you can now stick your solution there as a test function after smoothing. So we apply the smoothing operator to our solution. So first of all, we smooth by lambda, and then another smoothing is necessary because this is still h minus 1 valued. We need 2 valued, or even h1 valued for almost all times. So we take this test function, and then we can prove by letting lambda go to infinity uniqueness, which is kind of strange. This is possible, but in this inequality, it really works. But it's really hard, so it took us a long time to get this going. Okay, so this is the way how we get uniqueness. I want to skip this part. I have 7 minutes. Is it correct, Chairman? I started 5 minutes late. 5 minutes late. Yep. Okay. Just want to make sure. Okay, then I can explain the extinction result. So we can prove the following thing. This is very reminiscent of the porous media case. So if you have n between 2 and 3, n equal 1 is also true. You can find in another paper, but there you prove extinction not in L1 norm, but in L2 norm. L1 norm doesn't work. Yeah. So therefore, I have not taken it into the formulation because you see we prove here really in extinction in Ln norm. So n is dimension 2 or 3. Okay, so we take an initial condition in Ln. For n up to 3, we are allowed to do that. Then we look at the first extinction time in Ln norm. Okay, so then it follows that this time, extinction in Ln, this random time, the probability of this being less than t is big. If this is small, yeah, then it's big. If this is small. But if t goes to infinity here, then this is generally big. So we get extinction if we need to be careful in the limit. This becomes smaller than 1, which is exactly the case if the initial norm is smaller than rho. I will explain rho in a moment. And C star is the strength of the noise, basically, times dimension. Okay, in this case, it would be in 3, it would be times 6 or whatever. Okay, so the strength of the noise is here. If the noise is very strong, you have to start close to 0 to get extinction. Yeah? If this is larger, you have to start closer. Now, this rho is I don't know, I have no physical interpretation for this constant. And this is exactly what is important for this extinction proof, is we have to look at the embedding of ln over n minus, sorry, of w11 into ln over n minus 1. This is a continuous embedding. And we have to look at the continuity constant of this guy. So how good is this constant, depending on O, of course. And we take the inverse of this constant. This is exactly this rho. So it's the inverse of the constant of the embedding of w11 into ln over n minus 1. That appears there. I have no physical interpretation for that. It comes from our method. Of course, in the deterministic case, when the C star here is 0, yeah, 0, then you have no condition. Yeah, it's infinity. And, yeah, okay, this is true. And then you have, of course, probability. If you have extinction with positive probability, then in the deterministic case, you have the extinction. Yeah? And we can also calculate the extinction time. We have a bound. So we recover everything from the deterministic case. However, we need this condition n less than 3, and this has to do because our solution, the derivatives of our solutions, our approximating solutions, x lambda, do not have good integrability properties. This depends on dimension by Sobolev embedding, and then n equal to 3 is exactly the threshold where the usual stochastic so the Ito formula for the P norm breaks down. Okay, so that's the result, and just thinking what I can tell you about the proof. Maybe just the lemma that is the co-lemma. Yeah? So the co-lemma is this. So what you do, I go to the next page, you write down Ito's formula for the Ln norm. So here we use Coulomb. So you get this formula. You can see, I mean, this is the typical things you get when you do Ito formula for a P between S and T. So S is less than T. Now, if you look at this term, this was an approximation of the sine function here. So that means this is, so here I repeat the term, forget about this lambda, this comes from the plus lambda x lambda, which is not important. So the central part is this part. Yeah. So then simply write here grad x divide by grad x norm. So that gives you grad x squared divide by grad x norm. So what you end up with the grad x here. Okay. So now you can use the chain rule and put this under the gradient. So you get this term. Forget about this one. Lambda will go to 0. This will be good at the end. So you're here. Look at this term. But now you know by Sobolev embedding, this is in W11. So this can be estimated by the n over n minus 1 norm. Okay, so that means this, if you take the integral, and this appears with an integral here, if you take the integral, it's on the left-hand side, you can estimate from below, you can estimate from below by this norm. Okay, so at the end, you get, instead of the gradient, you get some ln over n minus 1 norm, and if you do the constant, I mean the exponents here right, you end up with this term. So now look at the lemma. So we have this kind of estimate. So the next thing I'm going to do, I'm going to take the nth square root of this guy and use the Ito's formula for the n square root in a smooth way. So then this n is gone. But then if you take the n square root of this, n square root of this, so comes out here is the first order of this guy. So then you will just get the n norm, so first order. But what you will get here, they will cancel out. So you will just get 1. It will be cancelled out. But it's only 1 where this is not 0. So you get the indicator function where this is not 0. And that helps you to prove this extinction. Maybe I stop here. Thank you.
Thank you very much.
In fact, for establishing well-posedness of the equation, you work directly on the first equation, not on the transformed one.
Right. But the uniqueness we were not able to do for the untransformed one, simply because we had to smooth. And if you take a smoothing operator, it messes up the noise, because the noise is linear multiplicative. So if you apply an operator to that, it will be a nice operator in front of the noise, but it will no longer be linear multiplicative. And that messes up the variational inequality. But if you go to the transformed equation, there is no noise. Yeah? And then, of course, there's an error term, but that can be controlled. It's much better than the other term. So we found no way to prove uniqueness directly from the stochastic equation. It's a
for instance, if you take the Satonovich one, then you don't have the mu, the remaining term.
But this is the same difficulty. I know that probabilists would always tell, I mean, probabilists, I'm also probabilist, but people really from the old school of stochastic analysis, oh, you should always take minus the bracket. But this term that comes out there is very good sometimes. So for instance, for asymptotic extinction results, if you have strong noise, you can read off that term that you have asymptotic extinction. So that means if you take Stotanovich, if you like, then it's difficult, more difficult, because this term is not there. Yeah? You're right. And I wanted to say about this extinction result, the lemma was for the approximating solutions. And you might get suspicious, because if you want to prove extinction for limiting process, you prove it for the approximation. There's no way directly that you can hope they get extinct, and then you would like to have an extinction run for the limit. You would not expect it. It's very difficult to control the stopping times. But what we actually, we go to the limit basically in this equation. And then this behaves very, very nicely. It's just lemma of Fatou. If you have extinction for has this inequality for the approximating ones, you have it for the limit. So there's a new trick which we did not realize in earlier papers. So it's very, very easy to go from the approximations to the limiting process by Fatou propagation.
Do you have a stochastic comparison principle between two solutions?
So actually, in this case, we didn't try. We tried in the porous media case, and with the stochastic term, we could not do it. We can only prove positivity. We tried very hard in another paper to have a comparison. I would expect we have, and maybe Benjamin, you have midway, right? For the stochastic porous media case, maybe we have. But it's not the usual. So usually, if you have positivity, you have also comparison principle. But for the stochastic porous media, it's not direct, but Benjamin solved it. And here we haven't tried. So that's the situation.
Because, I mean, this kind of changes the picture a little bit, because you could, I mean, for this type of equation, omega is not really important.
After transformation, you see that, yeah.
No, I mean, it's also not important, because you can put the boundary data the initial data discontinuous.
Ah, you mean the underlying set? Oh, okay.
Right. And you can put your O wherever you want, right? So it's basically an equation. It's because it has finite speed of propagation. It's an equation in Rn, even if it looks like an equation in a bounded domain.
But you have to prove this finite speed of propagation in the stochastic case. This is not
which you can do if you, I mean, just by comparison with 1D solutions, and then you are back to the original porous medium equation without any gradient in there.
You mean here also in the fast diffusion case?
Well, yes. I mean, once you have this
Comparison.
then you can.
Yeah, it's a good idea maybe too.
I think this is not fast diffusion. Fast diffusion is usually when.
No, it's not fast. It's not fast. It's not porous media.
Slow.
So this is called singular diffusion.
Singular, right? Fast diffusion is usually the other case.
That's the other case.
Infinity case. It's not fast.
Last version.
Yeah. How does the noise enter in the equation? You work with W once as a field, as a random field, and secondly, you integrate with respect to it. So is there the entrance by every psi, or is it in the classical sense?
It's always in the classical sense. Yeah? It's just when we do the transformation, we have to unravel it, because at some level we have to apply Ito's product rule in a rigorous way. But that's always the problem with SPDE. If you have not additive noise, is always the problem when you want to basically do a deterministic version of it. Is always the problem to fix the psi. I think Toucheng, they went into they did similar things from a linear multiplicative noise, but they went into an operator space, and apply the eta formula, roughly speaking, eta formula up there. That's another possibility. But we do it psi-wise, which is more direct. You can read it of the Brownian motion. And to make it rigorous, we have to do smearing out.
All the integrals are in the usual sense.
All are in the usual sense, correct. But we have to use stochastic for B all the time in order to go back to psi. But that is usual, what you have to do. Usual.
So let's thank Michael again.